When you see massive construction equipment or think about the landing gear on a huge airliner, there's this invisible force doing all the heavy lifting. It's a fluid, under incredible pressure, making things move with just immense strength and pinpoint accuracy. Today, we're diving deep into that unseen force, hydraulic oil. I mean, it's a question that almost sounds impossible, right? How can something that you can pour, something that flows and spills, act with the same power as a solid piece of steel? How does a liquid get to be so powerful and so precise? Well, that is the central mystery we are going to unpack. And nope, the answer isn't magic. The real secret is in the very specific, highly engineered characteristics of the fluid itself. This isn't just any old oil. It's a super complex liquid designed to perform under some of the most extreme conditions you can imagine. Okay, let's get into it. The best way to think about hydraulic oil is as the lifeblood of a machine. Seriously, it flows through all these steel veins and arteries, and it transmits power and commands. But for it to do its job, it has to have a really particular set of skills. And probably the most important of all of them is viscosity. Now, viscosity is a fascinating thing because in this whole story, it's both the hero and the villain. It is a classic double-edged sword. On one side, it's absolutely essential for protecting all the moving parts. But on the other, it's one of the biggest reasons for energy loss and inefficiency. So what even is viscosity? Well, the slide gives you the technical definition, but all you really need to remember is this. It's the oil's thickness. It is its fundamental resistance to flowing. And this picture here illustrates it perfectly. Just imagine the oil is like a deck of cards between these two plates. The force you need to slide that top plate, well, that's a direct measure of the oil's viscosity. It's the friction that's happening inside the fluid itself. So this is the big trade-off. You need the oil to be thick enough to have high enough viscosity so it can create a protective film between all those moving metal parts. But if you make it too thick, it gets really hard to pump, and you end up wasting a ton of energy just moving the fluid around. It is a constant engineering battle. And those downsides are a really big deal. Every single time that fluid gets pushed through a pipe or squeezed through a tiny valve, its own internal friction is fighting back. All that resistance just creates heat and wastes power, which, you guessed it, lowers the whole machine's efficiency. Now, if it was just as easy as picking one number and calling it a day, this would be a short explainer. But the real world introduces two major enemies that are always, constantly, trying to change the oil's viscosity while it's trying to do its job. Okay, what's really fascinating here is how these two forces work against each other. On the left, you see that as the temperature shoots up, the oil gets thinner. Its viscosity totally plummets. But then on the right, as the pressure builds up to thousands and thousands of psi, the oil molecules actually get squeezed together and its viscosity goes up. An engineer has to account for both of these things happening at the same time. It's wild. All right, let's move on to the next critical property, which builds on this whole idea. For a hydraulic system to feel snappy and precise, the fluid inside has to act like a solid steel rod. It has to be incompressible. We want what's called a stiff system, where if you push on one end, you get an immediate reaction on the other. Now, the fancy technical term for this stiffness is the bulk modulus. A high bulk modulus is exactly what we're looking for. It just means that even under crazy amounts of pressure, the oil's volume barely changes. It resists being squeezed, and that's what allows it to transmit force instantly. So, in theory, mineral oil is very, very hard to compress. For most practical purposes, we just say it's incompressible. But that ideal state is incredibly fragile. All it takes is one super common contaminant to ruin absolutely everything, and that contaminant is air. Okay, this graph is just stunning. That top line where alpha is 0, that's pure oil, super stiff. But just look what happens when you introduce just 1/10 of 1% of air. That's the line where alpha is 0.001. The stiffness, the bulk modulus, completely collapses. It falls off a cliff. Your system goes from being a solid steel rod to a wet sponge. But trust me, it gets much, much worse. This is one of the most incredible details from the source material. Get this. When that spongy, air-filled oil gets compressed really fast, the air bubbles inside are squeezed so quickly that they heat up to the point of ignition. This is called the diesel effect. You get tiny, spontaneous explosions inside your hydraulic system. It damages seals and breaks down the oil. Just amazing. So, beyond just viscosity and compressibility, there are these other hidden forces at play, kind of like a trio of troublemakers that can cause really serious problems if they aren't managed the right way. First up, density. This one's pretty simple. It's just how heavy the oil is. A denser fluid has more inertia, which just means it takes more energy to get it moving and to get it to stop. It also plays a big part in pressure losses when the fluid has to speed up to get through tight spots in the system. Next is thermal expansion. Like most things, oil expands when it gets hot. Now, if that oil is just sitting in an open tank, that's no big deal. But what if it's trapped inside a sealed hydraulic cylinder that's just sitting out in the sun? That expansion has nowhere to go. A pretty small temperature change can generate enough pressure to rupture hoses or even crack the steel cylinder itself.
And finally, we've got vapor pressure. We usually think of boiling as something that happens when you add heat, but you can also make a liquid boil just by dropping the pressure. In certain parts of a hydraulic system, like the suction line going into a pump, the pressure can drop so low that the oil itself starts to form vapor bubbles. And this leads to a nasty phenomenon known as
Cavitation. This stuff is the silent killer of hydraulic components. Those little vapor bubbles that form in the low-pressure areas get sucked into the high-pressure side of the pump. And once they're there, they don't just shrink, they collapse violently. The implosion is so powerful, it's like a tiny hammer blow, literally blasting away little pits of metal from the inside of the pump over time.
So, as you can probably tell by now, choosing the right hydraulic fluid is not about just maximizing one thing. It's an incredibly complex balancing act between dozens of different, competing requirements.
And we haven't even had time to really get into all of these. I mean, the oil has to lubricate, it has to prevent wear, it has to stop rust, it has to resist breaking down from heat, it has to work with all the different seals and paints, resist foaming up, and on top of everything, it has to be absolutely perfectly clean. The list of demands is just huge.
So, let's wrap up with the really crucial points here. First, hydraulic oil isn't just oil. It is a precisely engineered tool. Second, viscosity is the ultimate balancing act between protection and efficiency. Third, you have to keep air out. It makes the system feel like a sponge, and yeah, it can be explosive. And finally, those hidden killers like cavitation can literally eat metal for lunch.
All of this leaves us with one last question to think about. We are constantly demanding more and more from our machines. More power, more speed, better efficiency. So what does the future hold for these fluids? Are we going to see new synthetic oils with unbelievable stability? Or maybe even smart fluids that can change their own properties on command? The evolution of this unseen force is far from over.